Welcome to Calculus. The first part of Calculus is a review of some of your Algebra 2 and Pre-Calculus topics, including Section 1 here in the prerequisite chapter on graphs and models. This correlates very closely with the textbook with different examples so that you can look at the examples that are not only in the textbook but also look at the examples that are in the videos that I am creating. It starts off talking about the two main contributors of calculus, Wilhelm Leibniz and Isaac Newton. Descartes, though, René Descartes, you may remember René Descartes from your algebra days, was the gentleman who kind of set everything up with the development of coordinate geometry. So you should remember a little bit about the coordinate axes, ordered pairs, equations with two variables, slopes of lines, midpoint formula, distance formula, and so on. So we're going to do a quick review, and I'm going to try to make it quick because I know that these videos can be more than just a little bit boring. But I'm going to do a quick review here with some graphs. Now, don't become too dependent on using your graphing calculator or using decimals. Understanding and being able to use the graphing calculator is very important, but not at the point where you kind of sacrifice your skills at being able to graph without the use of technology. So we consider the equation y equals 3x plus 5. The ordered pair 1, 8 is a solution of the equation because when you substitute it in, it actually satisfies the equation or makes the equation true. So I have to apologize for the looks of my hand here as I'm setting up these videos, but I've been doing a lot of yard work lately and I got kind of roughed up a little bit. So sorry about the rough use there, the rough look. So I'm going to substitute the point 1, 8 because we know that this is your x coordinate and this is your y coordinate, and I'm going to substitute them in for the x and y variables accordingly, and I get 8 is equal to 3 times 1 plus 5. I get 8 is equal to, now of course 3 plus 1 is 3 plus 5 is 8. That makes it true. So when you get a true equation here, after substituting it in, that means it's a solution to the equation. All right, now we know graphically, and this is of course where Descartes came in, that this is the equation of a line and that's a point on the line. Now there are all sorts of ordered pairs that are going to make this true. 1, 8 is just one ordered pair. Because we know it's the graph of a line, we also know that it has infinitely many points, infinitely many ordered pair solutions. So a lot of times, especially when we're unsure on what the graph is going to look like, now we should have the lines down pretty well, is that we will set up a table of values and we will use that table of values to come up with a sketch, to come up with a graph of the equation. All right. Now, if you're given an equation that maybe you're not so familiar with, it says to create a table of values, you may have to plot a lot of points until you can get what the basic shape is. Now, the one drawback to graphing this way, of course, an equation that you're unfamiliar with, is that you may have to graph a lot of points. So you could use a graphing calculator to kind of get a rough idea of what's going on, but don't just try to copy the image on your graphing calculator and put that down. If I ask you to do a graph, I expect you to plot points and I expect you to be able to come up with as accurate a sketch as possible. And of course, when you're graphing, I expect you to be able to graph using graphing paper to make it a little bit easier for me to check. Also, I expect you to use a straight edge when you're drawing out your axes, and of course to set a scale, as here I've done in this first example. All right, now y equals the square root of 4 minus x squared. I think you should know what this looks like, but perhaps you're a little, it's been a few months since you've done any real work on this type of an equation, so maybe you're a little rusty. Although it looks like I misspelled range here. I got wrangle. There we go, range. So I have a domain from -2 to 2. Remember interval notation here, because if I plug in any number that's not in this interval, I'm going to get the square root of a negative, which is of course an imaginary, and we're graphing on the real Cartesian plane with the real number lines and such. Notice here, x-axis, y-axis. Notice here, everything measured out halfway decent. Graph paper would be better. And of course, set your scale. I put the scale down for the x-axis and the y-axis to indicate that each one of those tick marks is worth 1. The range for this, it turns out to be between 0 and 2, because the largest expression that I could come up with under the radical would be 4, and the square root of 4 is of course, is 2, and the smallest expression would be 0 because I can't get a negative, and the square root of 0 is 0, so I'm going to get these values here. Now if I plot some points, and I'm going to pick points from my domain here, and I've got them already set up with a t-chart. I substitute -2 in, I'm going to get 0. I substitute -1, and now don't forget, -1 squared is +1. That does not mean you take the opposite of -1 and then square it. You're subtracting whatever x squared is. So -1 squared is 1, 4 minus 1 is 3, so this is the square root of 3, which is approximately 1.732. I plug 0 in, I get the square root of 4, because 0 squared is 0. I plug 1 in, I get the square root of 3. I plug 2 in, and I get 0. So I'm going to graph these and hope that I can come up with an idea of what the actual graph is going to be. So I graph -2, 0, which is right here on the x-axis. I graph -1 square root of 3, and I have to approximate this, so I'm going to approximate it to be about here, because I think that's probably pretty close to 1.732. 0, 2 is right here. 1, this actually could come over a little bit. Try to be as careful and as neat as you can with your graph. If I plug 1 in, I'm going to get about here again. See, it kind of matches up height-wise, and if I plug in 2, I get 0. Well, to me, this looks like a semicircle. Now, if I had any kind of artistic ability at all, you would see that that looks more like a semicircle instead of part of an ellipse, part of an oval. Now, this next guy you should be familiar with, because I can think back to your Algebra 1 and Algebra 2 days that you've sketched graphs of equations that look like this. You probably remember that this is a quadratic equation in 2 variables, and that you will end up with a parabola. Now the domain of this is going to be all real numbers, because I won't have any square roots to worry about, and I don't have any variables in the denominator to worry about, so the domain, implied domain, is going to be from -infinity to infinity. Well, I'm not going to plug in that, that's infinitely many points, so I'll plug in a few to kind of get an idea of what's going on. So I plug in -2 here. Now I'm going to go ahead and actually show the work. Y equals -2 squared minus 2 times -2. -2 squared is 4. Minus 2 times -2 is going to be plus 4, so I get 8. I plug -1 in, so that's going to be 1 plus 2 is 3. I plug 0 in, I get 0, goes through the origin. Remember, the origin is 0, 0. I plug 1 in, I get -1. I plug 2 in, I get 0. I plug 3 in, I get 9 minus 6, which is 3. And if I plug 4 in, I get 16 minus 8, which is 8. And if you look at the y values here, notice the pattern that it's kind of the same 3 values here above as below. So I'm going to have some symmetry here, which makes sense because this is the graph of a parabola, and we know that they have an axis of symmetry. So -2, 8, 2, 3, 4, 5, 6, 7, 8. I put a little 8 here to remind me. -2, 8 would be approximately here. -1, 3, 0, 0, 1, -1, 2, 0, 3, 3, and 4, 8. And hopefully you can see the U shape. That is the parabola that we've become familiar with. And I'll try to sketch it as neatly as I can. Always do your graphs. Please always do your graphs in pencil. That way, if you make a mistake, it's easy to erase. Now, if you go ahead and you do your work and then you want to make like a final copy before you submit it, and you do that in pen, again, just be very neat. I prefer pencil if at all possible. I know some of you guys are kind of pen people. So let's move that off to the side, and let's consider some themes that are going to help us with graphing, such as finding intercepts. Well, I got to get the piece of paper up there first. Here we go. To find the x and y intercepts, of course, that's where it crosses the x and the y axis. We can find those by plugging 0 in for x or 0 in for y. Now, to find the x intercepts, where my graph crosses the x axis, I plug 0 in for y, and I solve for x. So I would get 0 equals 2x to the third minus 8x. I can factor here, and I'm going to flip-flop the sides. I get 2x times x squared minus 4 equals 0, or I get 2x, x minus 2x plus 2, 2 equals 0. So I'm going to get 2x equal to 0, x equal minus 2 equal to 0, and x plus 2 equal to 0. So I'm going to get x equals 0, I'm going to get x equals 2, and I'm going to get x equals negative 2. Now, if I'm going to write out the intercepts, I am going to write those as ordered pairs, because remember, these are the x values, but I plugged y in for 0. So the ordered pairs are 0, 0, 2, 0, and negative 2, 0. Now to find the y-intercept, I plug 0 in for x and I solve for y. Well, you can probably already see it coming, right? So I plug 0 in for x, and that would give me y equals 2 times 0 to the third minus 8 times 0. So I would get y equals 0. So the x value is 0, the y value is 0, my y-intercept is 0, 0. Now if it says find the intercepts, you don't have to write them twice, because it doesn't say identify the x-intercepts and the y-intercepts individually. If it did, then of course you would write it twice. Another thing that can help you with graphs, of course, would be able to determine symmetry, as I mentioned before with the parabola. Now, there are a variety of tests, and you can make adjustments for pretty much any kind of line that you would like, or any point that you would like, but the main lines that we consider, of course, are the x-axis and the y-axis, and as far as a point, we would like to consider, if a graph is symmetric to the origin. So I've written the test down, but I'm going to show you an example here in just a moment on how to use those tests. Actually, maybe a couple of examples. The test for symmetry for the y-axis says the graph of the equation in x and y is symmetric with respect to the y-axis if you replace x by the opposite of x and you get back to the original equation. Now, to see if it's symmetric to the x-axis, which means it wouldn't be a function, but we would still have a graph. The graph of an equation x and y with symmetric is symmetric with respect to the x-axis if replacing y by the opposite of y yields an equivalent equation, or gets you back to the original equation. And symmetry with respect to a point, like the origin, says the graph of the equation in x and y is symmetric with respect to the origin if replacing x by the opposite of x and y by the opposite of y yields an equivalent equation. Now, real quick here, and I'm going to just roll this back before I do my example. We already talked about symmetry with a line. If you have a line, your graph is symmetric, and I just drew a vertical line here. Your graph is symmetric to a line if I can pair up, and hopefully I did that okay, for every point that's not on the line, for every point that's on your graph, I can find a second point on the graph such that if I connect them with a line segment here, that the line of symmetry is a perpendicular bisector. Okay, whether it's with respect to the x-axis or the y-axis, and with respect to a point like the origin, a graph is symmetric to the origin, and I'm just going to draw one here, and I'm going to try to draw one that looks halfway decent here. By the way, on your axes, when you're drawing these out, you should have arrows because they are lines. I have a tendency to hurry through that, and I know some of you guys do as well. So be sure to put set your axes up properly. Again, straight edge, set your scales on both axes, and so on, and put arrows on the ends. So in this case, you have symmetry to a point like the origin if for every point that's on the graph, there exists another point on the graph, such that if you draw the line that connects those 2 points, that line segment, that the point of symmetry is the midpoint. Okay, so now let's go back to here. I don't have a graph, but I do have an equation, and I want to use the test for symmetry here. Let's bring this down just enough so that I can see the third. There we go. I see all 3 tests. Now, if I'm going to check first with respect to the y-axis, here I'll put it down here, y-axis. I'm going to replace x by the opposite of x and see if I get back to the original. So that would be y equals the opposite of x to the third plus the opposite of x. Well, the opposite of x to the third is the opposite of x to the third minus x. And if I factor out a -1, and see, I don't quite get back to the original. I have this extra factor of -1. It's close, but no cigars. So is it symmetric to the y-axis? No. And be sure to state yes or no, because if all you leave is the work and I have to interpret that, I think that means the problem's incomplete. You want to make sure you answer it. Now here, for the x-axis, I plug in the opposite of y in for y, so I would have the opposite of y equals x to the third plus x. And again, even if I multiply both sides by -1, I'm right back to where I was here with that extra factor of -1. So is it symmetric to the x-axis? No, it is not. Now the origin, and you may already see it coming. Let me slide this down just a little bit. For the origin, I'm going to check to see if I have symmetry. So I replace x with the opposite of x and y with the opposite of y. That would give me the opposite of y equals the opposite of x to the third plus the opposite of x. So I would have the opposite of y equals the opposite of x to the third minus x. So I would have the opposite of y if I factor out a -1. And then look what happens. If I multiply both sides by -1, I get back to the original equation, an equivalent equation. So that means that this has symmetry with respect to the origin. So I'm going to write in a yes here. Okay. That's what you have to do. Now, if they ask you to test for symmetry, don't just graph it on your graphing calculator and then look at the graph and say, oh, x-axis or y-axis. If they ask for the test, then show all the work. All right, here's another guy. I want to check for symmetry here as well. So for the y-axis, I plug in the opposite of x. So this would be y equals the opposite of x to the second power all over the opposite of x to the second power plus 1, where the opposite of x times the opposite of x, a negative times negative is positive. I get y equals x squared all over x squared plus 1, which is the original. So y-axis, yes, I do have symmetry. To check for the x-axis, I plug in the opposite of y. The opposite of y equals x squared all over x squared plus 1. Even if I multiply by -1, I have this factor of -1 that I can't get rid of, so I can't get back to the original, and the answer is no. And for the origin, hopefully I left enough room, I plug in the opposite of x in for x, the opposite of y in for y. I get the opposite of y equals the opposite of x squared, quantity squared, all over the opposite of x, quantity squared again, plus 1. This is the opposite of y equals, well, from the first example, this just becomes x squared over x squared plus 1. And then actually from the second example, if I multiply both sides by -1, I cannot get back to the original. I have that extra factor. So in this problem, I have symmetry with respect to only the y-axis. Now, let's use this information for intercepts and such, and also we'll set up a t-chart if we need to sketch the graph of x equals y squared minus 4. Now, the intercepts, to find the x-intercept, I plug y equals 0 in, so that would give me 0 squared minus 4, so I would get x equals -4. That would mean I would have the x-intercept at -4 is 0. That's good to know. And then also the y-intercept, to find the y-intercept, I plug x equals 0. So I would get 0 equals y squared minus 4. 0 equals y minus 2 times y plus 2. So I would give me y minus 2 equals 0 or y plus 2 equals 0. And I would get y equals 2 or y equals -2. So I have 0, 2, and 0, -2. Those would be my x-intercepts, or excuse me, my y-intercepts. So I have my x-intercepts here, my y-intercepts here, and of course I didn't give myself very much space. For symmetry here, I'm going to kind of streamline this a little bit. I have x to an odd power, I have y to an even power. So that kind of gives me the idea that if I plug in the opposite of y in for y and squared, I'm going to get right back to y squared. So I have symmetry here with respect to the x-axis. If you check, you would plug the opposite of y in, and that would give me x equals y squared minus 4. which is my original equation here. So now I know I have some symmetry here to the x-axis. I have my intercepts. I want to plot a few points all the same, so I plug -3 in. Now notice here, this time I set up my t-chart. Well, first off, I put it on its side. That's okay, but I plugged in values for y instead of values for x because the x is already in terms of y. So if I plug -3 in and square it, I get 5. If I plug -2 in and square it, I get 0, which makes sense because there's that point right there. If I plug -1 in and square it, I get -3. If I plug 0 in and I square it, I get -4, which makes sense because I have -4, 0 here. If I plug 1 in and square it, I get -3. If I plug 2 in, I get 0 again. Oh, this one this time. And if I plug 3 in, I get 5. So if I plot these points, 1, 2, 3, 4, 5, here's 5, so I have 5, -3, that's down here. I have 0, -2, that's right here. I have -3, 1, 2, 3, -1, that's right here. I have -4, 0, that's right here. I have -3, 1, that's right here. 0, 2. Oh, I definitely have symmetry now with respect to the x-axis here. And then 5, 3. And I have a parabola. I just have a parabola that opens to the right. It's not a quadratic function, but that's okay. It's still a parabola. Try to be as neat as you can with the graphs. Okay? And I put the little arrows here to indicate that. All right, next thing. What if we have more than one graph? What if we have more than one equation? Would we be interested in all the solutions to both equations, or maybe just be interested in those solutions that satisfy both equations, or find their intersection? A point of intersection of the graphs of two equations is the point that satisfies both equations. You guys know 3 different ways, maybe 4 if you remember Kramer's rule, in which you can find the point of intersection of the graphs of two equations with two variables. So we can use the substitution method, we can use linear combination, sometimes called the addition method, or we can use the graphing method, which is okay, except that if your graph is off a little bit, your answer probably is going to be off a little bit. Find the point of intersection of the graphs of the equation. Because of the way, excuse me again, this system is set up, notice I have y equals x minus 1, y minus x squared equals -3. One of the equations already has one of the variables isolated. So what I'm going to do is I'm going to use substitution here, the substitution method, and I'm going to substitute x minus 1 right in for y. Now this should look really familiar because you did this way back in Algebra 1, Algebra 2, and last year in pre-calculus. I get x minus 1, that goes in for y, minus x squared is equal to 3. This is going to give me an equation with only one variable, which I should be able to solve. I'm going to bring because it's quadratic, I'm going to bring everything to the one side here. So I'm going to subtract x, add 1, and add x squared. And I get x squared minus x. Let's see, if I add 1 to both sides, oh, that's a -3. Almost messed up there. If I add 1 to both sides, I would get a -2, so minus 2. So this is going to give me x minus 2, x plus 1, x minus 2 equals 0, x plus 1 equals 0, the old zero product property, and I get x is equal to 2, x is equal to -1. So those would be the x values of my 2 points, notice plural, of intersection. To find the y values that go with them, I could plug back into either equation. I'm going to take the top one. It's simpler and it already has y isolated. Plug 2 in, I get a 1. Plug -1 in, I get a -2. Now this turns out to be a line, and this turns out to be a parabola. And as you might imagine, if you have this kind of situation, you could have 2 points of intersection. Excuse me. Now, we finished this by talking a little bit about applications in math, because calculus is all about applications. And we've done a number of story problems in our algebra days, and even geometry, and definitely pre-calculus days. So we want to make mention of the fact that we will need to be able to, at times, represent data with an equation. We have data that's given to us, and we want to come up with a mathematical model. The data comes from some kind of a real life application. It could be having to do with money. It could have to do with people's ages. It could have to do with half-lives, time, distance, velocity, and such. And so what we're going to want to do is be able to create an equation that models the problem. And if we're given data, maybe some ordered pairs, we want to try to make it as accurate as possible. Now, if you graph the data as ordered pairs and you get a line, it's pretty easy to come up with the equation of a line. We'll review it in another section. But a lot of times, this is where you would want to bring technology into play here and use your graphing calculator to find the line or the curve of best fit. Now, the good news is you won't have to do that on the AP exam. I'm not going to spend a lot of time on it, although I'm pretty sure that there's enough videos online that you can find that will show you how to find the line or the curve of best fit for the data. All right, be sure to do the practice problems and before you start working on the assignment that's going to be turned in to me. Be sure to show all your work. If you have questions, ask, and by all means, don't forget to practice, practice, practice.